Hi everyone. In this video, we're going to be talking about electrolytes and non-electrolytes. So first of all, let's go with some definitions here. An electrolyte is defined as a substance that conducts an electrical current in water. A non-electrolyte is something that does not conduct electrical current in water. Now, what does that mean at the molecular level? Well, an electrolyte typically consists of ions, like sodium chloride. When it dissolves in water, like we talked about previously, it separates into sodium and chloride separately. Because these have an electrical charge to them, this solution can conduct electricity, kind of like a wire. Now, a non-electrolyte is typically a molecule, a covalent compound that does not dissociate in water. So something like hydrogen peroxide, H2O2, this is a molecule. It mixes with water because it can hydrogen bond, but it doesn't break apart. It stays together as a whole molecule. And so there's no ions here. And so this is a non-electrolyte. Now let's look at electrolytes a little more in detail. We can define an electrolyte as a strong electrolyte if it gives 100% dissociation. So something like sodium chloride, every single bit of sodium chloride separates into sodium and chlorine. And so it's 100% separation. And so this image right here is showing a electrical current passing through a solution of sodium chloride. And you can see that the light bulb turns on because the solution is able to conduct the electrical current through it. So a strong electrolyte has 100% dissociation. On the other hand, a weak electrolyte is something that only has partial dissociation. Now, an example of this is hydrogen fluoride. So hydrogen fluoride dissolves in water because it's really polar, but not all of the HF molecules separate. Some of them stay together. And so here's a picture showing what happens if you try and run the same light bulb with a solution of HF. And you can see the light bulb turns on, but it's not super bright, indicating that only a little bit of electricity is able to pass through the solution. And the reason is because there's only a little bit of free ions. So most of the HF stays stuck together as a molecule, but some of it can separate. And so whenever you have a weak electrolyte, this separation is reversible. So the HF molecule can separate or it can reform. It can separate and it can reform. And so it's a back and forth equilibrium, as we call it, or a reversible reaction. So once again, weak electrolytes have partial dissociation. And then a non-electrolyte, like we mentioned before, has no dissociation whatsoever. It's a molecule that stays intact. So sucrose here, sugar. When you dissolve it in water, it's still sucrose. It's just aqueous now. It's surrounded by water molecules. And as you can see, if you try and run the light bulb, no electricity can pass through this solution because there's no ions. It's just molecules. So non-electrolytes have no dissociation. Let's do a quick study check. Complete each reaction for strong electrolytes in water. So we know that strong electrolytes give you 100% dissociation. So let's see what happens here. If we have calcium chloride and we dissolve it in water, because it's a strong electrolyte, it's going to split between the calcium and the chloride. And so you're going to have a calcium, which has a 2+ charge, and then you're going to have a chloride, but there's two chlorides. And so you're going to have Cl- and Cl-. Or you could just abbreviate that as 2 Cl-. Okay. And so it looks like this is going to be our correct answer. Now, what about potassium phosphate? Well, once again, it's going to separate between the cation and the anion. And so our cation is potassium, which is K plus. But because there's three of them, we're going to have three K pluses. And then PO4, we know is a polyatomic ion. And so it stays together as PO4, but it has a 3 minus charge. And so it looks like this is going to be the correct answer. So your polyatomic ion stays together as the polyatomic ion. All right, let's do another study check. Which of the following reactions represent a strong electrolyte in water? So remember, strong electrolyte has complete dissociation. So this top one here, that doesn't look like dissociation. That looks like a combination reaction. B, you have liquid CH3OH, and it's becoming aqueous CH3OH. That looks like a non-electrolyte because it didn't dissociate. D, same thing, no dissociation. But C, if you look closely here, the sodium sulfate separated into sodium and sulfate. So because you had separation of ions and they're still charged, that's going to be a strong electrolyte. All right, let's do another study check here. Write the equation for the formation of a solution for each of the following. The dissociation of potassium chromate, a strong electrolyte in water. So we're going to have K2CrO4, and it's going to be solid initially, and then we're going to mix it in water, and it's going to dissociate because it's a strong electrolyte. And so you're going to have two K pluses, and we're going to have a CrO4 2 minus. And these will both be aqueous because they're now dissolved in water. All right, part B, the partial dissociation of the weak electrolyte H3PO4 in water. And so you're going to have H3PO4 aqueous, and it's going to partially dissociate, which means it's a reversible reaction when you mix it in water. And it can give off the hydrogen. And so you can have H plus aqueous and H2PO4 H2PO4 just 1 minus. That'll also be aqueous. And so you can rip off one of the hydrogens and have them as separate ions, or they could reform. Now, the question's not super specific about how many hydrogens you could rip off. If you wanted to, you could have written this as 3 H pluses and PO4 3 minus. Same concept, right? You're separating positive ions from the negative ions. Either one of those answers would have been acceptable. Now for C, solid sugar dissolving in water. So this is a covalent molecule, so there's no dissociation. So all you do is take your chemical formula here, and it's solid, and when you mix it in water, you're still going to have the same chemical formula, but now it's aqueous. So it went from solid to dissolved, but it's still the same molecule. So non-electrolyte, weak electrolyte, and strong electrolyte. So the next thing we're going to talk about is something called equivalence. Now, this is a term used in the medical field, usually when we're talking about IV solutions. And so the definition of an equivalent is the amount of an electrolyte or ion that provides 1 mole of electrical charge, either positive or negative. Now, in solutions, the total amount of positive ions is always balanced by the negative ions. So the total amount of positive equals the total amount of negative. The total positive charge has to equal the total negative charge. Just like when you're balancing an ionic compound, same concept, but now they're dissolved. So the total amount of positive ions has to be the same as the total amount of negative ions. And equivalent is a metric unit, and so you can have milli equivalents, and one equivalent is 1,000 milli equivalents. So let's look at some various ions here. So sodium, because it has a +1 charge, if you had 1 mole of sodium, that would be 1 equivalent. But calcium has a 2+ charge, and so 1 mole of calcium is 2 equivalents of positive charge. Iron 3+ has a 3+ charge, and so 1 mole of iron 3+ is 3 equivalents, because an equivalent is the amount of charge. Chloride has a -1, so 1 mole of chloride is just 1 equivalent. Right? Sulfate is a 2- charge, so 1 mole of sulfate is 2 equivalents. So the equivalents correspond to the charge of the ion. And so as an example, if you had a solution with 25 milliequivalents of sodium and 4 milliequivalents of potassium, because these are both positively charged, you would add those together and you would say that you have 29 milliequivalents of positive charge. Now, if chloride was the only anion, it would have to balance that out. So you would have to have 29 milliequivalents of negative charge to balance out. So the total positive has to equal the total negative. So if you have 29 milliequivalents positive charge, you'd have to have 29 milliequivalents of negative charge. Let's do a practice problem for calculating equivalence here. So I'm going to switch colors. A laboratory tests a patient and it indicates that the blood calcium level is 8.8 milliequivalents per liter. How many moles of calcium ion are in 0.5 liters of blood? So let's set this up. We're going to start with the given value here. So 0.50 liters. And we're going to multiply that by a conversion factor. We want liters to cancel. And it looks like they gave us a conversion factor right there. There are 8.8 milli equivalents for every 1 liter. So liter cancels liter. Now we need another conversion to get rid of milli equivalents. And so let's get to regular equivalents. And so this is a metric unit. So 1 equivalent has to be 1,000 milli equivalents. Milli equivalents cancel. Now we have equivalents. And we need another conversion factor. And we want to get rid of equivalents. Now, we're talking about calcium ions. What's the charge on a calcium? Well, if you look at the periodic table, we know that calcium is Ca2+. So, based on this chart, right, if something has a 2+ charge, it's 2 equivalents per mole. So we can say that every 1 mole of calcium gives you 2 equivalents because it's a 2+ charge. And now equivalence cancels. Now we're left with moles of calcium, which is what we were looking for. So if we punch this into our calculator, let's see, we've got 0.5 times 8.8 times 1 times 1 divided by 1,000 times 2. And I get something like 0.0022 moles of calcium ion. Okay. And it looks like we did it right. Let's do another practice problem. Oh, let's get rid of the answer there. So a laboratory test patient and the blood calcium is 8.8 milliequivalents per liter. If chloride ion is the only other ion present, what is its concentration in milliequivalents per liter? So once again, the total positive charge has to equal the total negative charge. And they're telling you that the calcium is 8.8, and we know that calcium is a positive charge. So you have 8.8 milliequivalents of positive charge. So the negative charge has to be 8.8 milliequivalents. And so if chloride is the only negative ion, then you have to have 8.8 milliequivalents of chloride. So let's talk about blood plasma. You don't need to know this for the exam. This is just in case you find it interesting. So this chart is showing you the concentrations of different ions in blood plasma. So in your blood, you have sodium, potassium, magnesium, and calcium, which are positively charged. Sodium, you have about 138 milliequivalents per liter, so a lot of sodium. You only have 5 milliequivalents per liter of calcium, so of potassium, so barely any potassium. Magnesium is only 3, and calcium is about 4. So your blood ions for the positive charged things are mostly sodium with small amounts of potassium, magnesium, and calcium. Now the anions, the negatively charged things, it's mostly chloride, a little bit of bicarbonate, a little bit of hydrogen phosphate, and you actually have some negatively charged proteins to make up the rest. And what you should have noticed here is that the total positive ions are equal to the total negative ions, right? Total positive has to equal the total negative. So you have 150 milliequivalents of negative charged things and 150 milliequivalents of positively charged ions. Now, IV solutions need to somewhat match the ions that are naturally in your blood. And so here are some different IV solutions and what they contain. So there's a basic sodium chloride solution, which gives you 154 milliequivalents of sodium and 154 milliequivalents of chloride. They also have potassium chloride with 5% dextrose. So this gives you 40 milliequivalents of potassium and 40 milliequivalents of chloride. And you would give this to somebody who has low potassium to get their potassium back up. It's also Ringer's solution, which is a replacement for a lot more electrolytes. This is somebody who's suffering from like severe dehydration. It gives you sodium, potassium, calcium, and chloride. So it tries to replace a lot of them. There's also a maintenance solution, which gives you your electrolytes and a little bit of sugar, the dextrose. And that gives you sodium, potassium, chloride, lactate, and hydrogen phosphate. And then a replacement fluid, sodium, potassium, calcium, magnesium, chloride, acetate, and citrate. So different IV solutions provide different amounts of electrolytes. You don't need to know any of these. This is just in case you find it interesting. So let's do another study check. In 1 mole of iron 3 plus, how many milliequivalents are there? Well, the iron has a 3 plus charge, so 1 mole of iron is going to give you 3 equivalents because it's got a 3 plus charge. Now, 2.5 moles of sulfate is going to give you how much? Well, there's a 2 minus charge, and there's 2.5 moles. So if you multiply those, you're going to get 5 equivalents. An IV bottle contains sodium chloride. If the sodium is 34 milliequivalents per liter, the chloride has to be, well, once again, total positive has to equal total negative. And so if you got 34 of sodium plus, then you're going to have 34 of the negative charge. Positive equals negative. Okay. So that's it for this video. Thanks for watching, and I'll see you in the next one.